I'm going to talk about a basic introduction to quantified Boolean formulas, what they mean, and just give a basic overview. So I'll start. Boolean variables and logical operations, what I'll need, so I'll define. So a Boolean variable is just any variable which can take 0 or 1 values. So x is a Boolean variable, x equal to 0 or x equal to 1. These are the only two values allowed. And if the first logical operation is when I say x bar, I mean not of x, which is basically I say x bar is true if x is 0 and x bar is false if x is 1. The second is x or y. So x or y is true if either x or y or both are true, and it's true or 1 and 0 or false, and if x or y is false if both are 0. And x and y means x and y is true if both x and y are both true, and it's false if even one of them is 0. So this is basically x bar, x or y, and x and y are the three basic logic operations I'm going to use. And I'm going to use them to define a Boolean formula in CNF. CNF is basically giving a structure. It's called conjunctive normal form. It's just basically giving a structure to my formula, and I'll explain what the structure to my Boolean formula is. So I'll define something called a clause. So a clause is basically just an OR of literals. What do I mean by literal? So every variable can either appear as either as x or as x bar. So these are my two options for a variable appearing, and so I call this a literal. X and x bar are my two literals for a given variable, and a clause is basically just an OR of literals. So x or y or z bar, this is a clause, but if I say x or y and z bar, this is not a clause. So, and I say a formula is in CNF if I have an AND of clauses. So x or y, y bar or z bar, x bar or z. These are three clauses, and I have an AND of these three, so this is just a basic Boolean formula in CNF. So given a formula, what am I interested in? I am interested in whether my formula is satisfiable or not. What do I mean by this? Is this formula satisfiable? Is there any assignment to my variables x and y such that when I plug in the assignment to my formula, this formula evaluates to true? So the question I am asking is, does there exist an x and an y such that x or y and x bar or y bar is true? The answer is yes. Why is that? Because say I have x equal to 1 and y equal to 0. So x equal to 1, the first clause x or y becomes true, and if I y equal to 0 tells me x bar or y bar is also true. So true and true gives me true. But suppose I have this formula, there exists x and we have these four clauses. I am saying this formula is not satisfiable. We can do a quick check to say why. Because say x, y, we can say we have two variables, so we have four possible assignments 0, 0, 1, 1, 1, 0, 0, 1. So if I have 0, 0, then x or y becomes 0. So 0 and anything is always false. If I have 1, 1, then the second clause becomes 0. So again, if I have 0, 1, the third clause becomes true. And if I have 1, 0, the fourth clause becomes false. So for all possible assignments, this formula always evaluates to false. So there is no assignment such that this formula becomes true. So this formula is unsatisfiable. So a way to look at this is, we say in the CNF formula, a formula is true if given an assignment, a formula is true if and only if the assignment makes all my clauses to be true. Because even if one clause becomes false for my assignment, the entire formula, because 0 and anything is always false, my formula will become false. And a clause is true if just one literal or just one variable in my clause is true, then my clause becomes true. So basically, given an assignment, a formula is true if there is at least one literal in every clause that is true. So this is the notion of satisfiability of a formula. So now moving to quantified Boolean formulas. What is quantified? So now a quantified Boolean formula is basically just a formula plus a quantifier prefix. What do I mean by a quantifier prefix? Earlier there was just there exists. Now we have the notion of for all. So we have two possible options, and for each variable in my formula I assign it either to be there exists or to be for all. So I ask the question, there exists x for all y is x or y and x bar or y bar. So now the question is not satisfiability anymore. The question is this formula true or false? That is the notion of my question. So here is looking at an example. If I say there exists x from the previous slide, I say that this formula is false. Why? If I look at x equal to 0, then for y equal to 0, my formula becomes false. And for x equal to 1, again for y equal to 1 the formula is false. So there does not exist any x such that for all y's my formula becomes true, therefore this is a false formula. But again if I just do something different, I have for all y there exists x and the same formula, this formula becomes true. Why is that? Because if I say y equal to 0 and then x equal to 1, then this formula is true. Y equal to 1, x equal to 0 again makes this true. So for every y there is some x which makes my formula true. So this is a true formula. So given we are interested in true and false, whether a QBF is true or false, one important thing to notice is in satisfiability just the formula is important. There is no notion of ordering, but the order in which I present my variables in a QBF is very important. Not just the quantifier, but also the order in which they are is something which is very important in deciding whether a formula is true or false. How can we look at that? So one way of understanding QBFs better is looking at it as a two-player game. So what is this two-player game? We have two players. We say the existential player and a universal player. What does the existential player do? He assigns values to the existential variables. The universal player assigns values to the universal variables. How do they do so? They do so in the order in which they appear in the prefix. The game ends when all the variables have been assigned a value. So let's look at a run of how a game can proceed. Suppose the existential player will first have to play x. Suppose they play x equal to 0. The universal player will choose u. They choose u to be 0 and the existential player chooses t to be 0. What happens is that the first clause, given this assignment of x equal to 0, u equal to 0, t equal to 0, the first clause becomes 0. So the formula on this particular assignment evaluates to false. So I say that the universal player wins the game. And a different run of the game can look at x equal to 0, u equal to 1 and t equal to 0. In this assignment all three clauses are satisfied. The formula evaluates to true. So I say the existential player wins this round of a game. A quick third round will show that on this assignment the universal player wins the game again. So if you observe carefully again as to why the order is important, we say u equal to x is a winning strategy for the universal player. Why is that so? Because the universal player u will always choose his value after x. Whenever u and x are the same, we can say that either x and u are both true or both false. So accordingly either t must be true. And the third clause tells me t bar must be true for the existential player to win. So in this case u equal to x, if the universal player plays like this, the formula will always be false. So this is what I say as a winning strategy. And if you look at it effectively, the goal of the existential player on this game is he is trying to satisfy the formula, the universal player is trying to falsify the formula, and the notion of true and false can be equated to a strategy on winning the game. A QBF is true if the existential player has a winning strategy, and a QBF is false if and only if the universal player has a winning strategy. So this is how we can, a notion of extending in true or false in general to a game or a strategy on a two-player game or a strategy. So going back, so this was basically QBF. So going back to basic satisfiability that we saw, we said that this formula was unsatisfiable. So why was it so? A basic idea of this formula or any other formula, an easy way is to look at the entire truth table. To give satisfiability, any one assignment which satisfies the formula is enough to say that the formula is satisfiable, but a single assignment which falsifies the formula is not good enough to say that my formula is unsatisfiable. I must show that there is no assignment which satisfies. So a truth table is a basic way where I list out all assignments and show that on every assignment my formula is false, so the formula is unsatisfiable. But is there a better way? So what we are trying to show is that there is no assignment such that we can satisfy the formula. To do that, there is a rule which we call the resolution rule. What does this say? Suppose I have a clause a1 up to ak or x in my formula, and I have a second clause b1 up to bl and x bar. What I can do is I can resolve them to get all the a's and all the b's and throw away x and x bar, and I say that I can add this new derived clause to my formula in a manner that if my original formula was true, adding this resolved or derived clause to my formula is still satisfiable. Why is that so? Because suppose if I look at the two clauses in the antecedents, if there is any assignment which satisfies both of them, it must be that one of the A's or one of the B's is true, because no assignment can have both x as 0 and x as 1. I am allowed to choose only one value of x. So either one of the A's or one of the B's, one of them must be 1 if there is an assignment which satisfies my formula. So that same assignment will also satisfy my derived clause, because that same A, B will again set my resolvent or my derived clause to 1, and therefore my formula will still be satisfiable. So doing this, I can add a new clause to my formula while maintaining satisfiability. And when do I say that my formula is ended? So we have this notion of an empty clause. What does it mean? This clause has no literals. So we say that there is no assignment which can satisfy this clause. So from that we say, if we can derive this empty clause using resolution, this means that the initial formula was unsatisfiable. Why is this so? Because we have always mentioned that if my antecedents were satisfiable, my resolvent has been is also satisfiable. So since this resolvent cannot be satisfied, my initial formulas was also unsatisfiable. So this is the notion, and given that this is a resolution proof on how we can show that my formula was unsatisfiable, we take the first and the third clauses, the y goes away, I take x, I add it to my formula. Then I take the second and the fourth, I can get x bar, I can add the same to my formula, and using x and x bar, I get empty. So I add empty to my formula, and once I have empty inside my formula, I say my formula is unsatisfiable, so my initial formula was also unsatisfiable. So this is one of the basic proof systems, we call the resolution of basic proof system, to show why a formula is unsatisfiable. It's a proof of unsatisfiability. So based on this, just proof systems are also not enough. We have what are algorithms. So CDCL is one of the many algorithms. How this proceeds is that it tries to construct a satisfying assignment. I am trying to prove either my formula is satisfiable or unsatisfiable. I try to find a satisfying assignment. Suppose I find a satisfying assignment, I am done. But in case I am not, I fail and I create some unsatisfying assignment. This unsatisfying assignment happened because I falsified some clause in my formula. From this, I learn something new. What this learning new thing does is it prunes my search space. Initially, from my 2 raised to power n potential assignments, I have pruned my search space, and I keep going until I hit either a satisfying assignment or I generate a proof of unsatisfiability. I'll skip over how to find, and this is how in general I've suppose trail 1 and trail 2 are my 2 tries of how the algorithm is proceeding. It fails. From its failure, it learns something and it keeps going, and ultimately it fails by learning or extracting a resolution proof of the empty clause. So this is basically from a run of the algorithm, I can derive either a satisfying assignment or a resolution proof which falsifies my formula. So what we want to basically do, this is the basic idea of how it works in proposition. When moving to QBFs, the notion becomes slightly more complicated. Resolution is drifted to a different proof system called Q resolution. CDCL, the algorithm extends to something called a QCDCL, which again determines truth or falsity. And what we work on basically, again, because QBFs must respect the order, we try to see, somehow, which puts a lot of restrictions on how the algorithms can proceed. So we try to see if somehow the order can be relaxed in some manner, and how relaxing the order in different ways affects the strength of my proof system and the strength of the algorithm, and how fast I can prove true or false. So this is the kind of idea behind doing QBFs. So thank you.
Thanks a lot, Abhimanyu. So